Now we will talk about some methods for observation of magnetic domains. The first signature of the presence of magnetic domains appears in Barcals and Noise. When we plot magnetic flux density or magnetic induction B versus the magnetizing field strength or magnetic field H, if we zoom into the hysteresis loop, we find that there are discrete steps in the hysteresis loop. So these discrete changes are signatures of domain walls that are going through discrete jumps as they sweep through the specimen. So discrete changes in magnetic induction that is detected by suitable amplification of the B signal with a search coil. This is called Barcals and Noise. And the discrete jumps arise from domain wall hindrances along its path. So we see that the domain walls are getting pinned and depinned in some crystal imperfections as they proceed through their path in the magnetization process or demagnetization process. Okay, so bitter method. So this is a direct observation of magnetic domains. We spread a liquid containing very fine magnetic powder suspension on a magnetic material surface. The particles will accumulate at positions where there is the largest magnetic field gradient. That is to say, we have free poles, and this is going to basically show us the domain wall structure. And most recently, there have been ferrofluids, colloidal solutions of ferromagnetic particles in a carrier liquid that are used for this purpose. In order to get a clean picture of the magnetic structure, we usually need to electropolish the surface to remove the strains that would reduce the size of the domains. So bitter method is spread a liquid containing very fine magnetic powder suspension on an electropolished magnetic surface. So that's the idea. The particles accumulate at positions with maximum magnetic field gradient. And here you can see one example. This is striped domains on a permalloy, nickel iron alloy 9010. You can see these striped domains forming nicely, and the magnetic particles are basically showing us the domain walls between these domains. Another very useful method is magneto-optic Kerr effect. This is based on the interaction of polarized light with magnetic moments at the surface. So we see a clean picture of the magnetic structure by looking at the rotation of the polarization of the reflected light from the surface, and that's called magneto-optic Kerr effect, and it comes in three possible configurations. So first of all, it is the rotation of the direction of polarization of a polarized light beam that is reflected. So reflected is an important word here because we also have a transmitted version. Reflected from the surface of the magnetic material This is called magneto-optic Kerr effect. So we have three possible scenarios depending on the direction of magnetization. So this is our surface, and let's say that it is magnetized perpendicular to the surface. So that's our easy axis. That means the rotation in the polarization direction will be determined by the right-hand rule. So it will be rotated like this. So if you have an incident polarized light and reflected polarized light, we will see that the direction of the polarization will move in this direction, and the effect that we see is called the polar effect, and this has the maximum Kerr signal. So this has the maximum signal compared to the case where I have the magnetization in the plane of the film, and with the right hand rule that causes a rotation of the polarization in this direction, and we see the incident light and the reflected light here. We're detecting the polarization of the reflected light, and the effect that we have here is the longitudinal effect. So this is the signal level is less than the polar effect, and now this signal level is comparable to this other scenario where I have the magnetization also in the plane of the film, but pointing towards us. So it's almost the same thing. So one is basically pointing in the long axis of the specimen, one is pointing in the short axis of the specimen, but still in the plane of the film, and this is called transverse effect. Transverse magneto-optical Kerr effect, and that has a signal level comparable to longitudinal effect. So for the best mock measurements, we need to look at specimens that have an out-of-plane magnetization. So here is one example from Soldato et al. Closure domains on nickel 81, iron 19. You can clearly see a nice contrast between different domains. Now the version that is based on the rotation of direction of polarization when the polarized light beam is transmitted through a thin film is called the magneto-optic Faraday effect. So the rotation of the direction of polarization of a polarized light beam transmitted through a thin magnetic film. This is the Faraday effect. It's a bulk effect. So a magnetooptic Kerr effect is a surface effect. Magnetooptic Faraday effect is a bulk effect. And the Bitter method works for the surface. The Barcals and Noise is due to the motion in the bulk, not just the surface. And so you can see here domain structure in yttrium iron garnet that has been detected using Faraday effect here with no field and with some field applied. So you can see it has a very, it's small coercivity, so it aligns in the direction of the field quite easily. The domains switch. Now, a very sensitive method with ultra high resolution is Lorentz microscopy. This is basically measuring the bulk of the film because we have electrons transmitted through the thin film that is giving us this effect. So this is in transmission electron microscope. Transmitted electrons are deflected when subjected to local magnetic field gradients The force is the Lorentz force, so it's minus mu0 ev cross with m, the magnetization in the specimen. The spatial resolution is typically 5 nanometers. So this is by far the best method to image domains. But what it does image is it images domain walls because the deflection of the electrons is due to magnetic field gradients. So we are imaging domain walls, and it's a bulk effect because we are looking at transmitted electrons. And here you can see domain structure of lanthanum calcium manganese oxide at 195 Kelvin. That is using the Lorentz microscopy. It's a very nice picture. You can see these, the presence of these domains using the Lorentz microscopy. Another method is spin polarized scanning electron microscopy. So we look at the number of backscattered electrons at a given angle, and this is dependent on the direction of magnetization within a domain. So it is basically measuring the domain structure at the surface. So we have a surface effect here. We're looking at the reflection of electrons from the surface, the number of backscattered electrons or secondary electrons at a given angle is dependent on the direction of magnetization within a domain. So here we're imaging the domains directly. So you can see one example, domain structure in single crystal cobalt here. This was done by Hitachi. Hitachi SAMPA, scanning polarized scanning electron microscope, spin polarized scanning electron microscope. And another method is neutron diffraction. This is also quite useful. We have a beam of polarized neutrons that passes through a specimen and so it's basically transmission mode. So this is again a bulk effect. And the angle of rotation of polarization so that's the polarization of the neutrons that is being detected. Neutron has a magnetic moment but no charge. So it's a pure magnetic effect. The magnetic moment of a neutron is of the order of 5 times 10 to minus 27 ampere meter squared. The Bohr magneton, if you remember, is 9.27 10 to minus 24 ampere meter squared, which is of the order 10 to minus 23 ampere meter squared. So there's orders of magnitude difference between the magnetic moments. And last but not least, we have magnetic force microscopy. We have a small tip here, a small 10 to 100 nanometer radius magnetized probe tip. This tip is scanned over the surface and we detect the variations in frequency and phase of the oscillations of the tip. The resolution we can get typically is 50 nanometers. So using a smaller radius tips, it's possible to get a better resolution. Once again, this is a surface measurement. The surface magnetization, however, can be affected by the presence of the tip. So we have to be careful in using a low moment tip. The surface magnetization can be affected by the tip. So this is a potential problem, and images, this method images not the domains but domain walls, because we see the variations in the frequency and phase in large magnetic field gradients. So other techniques that work in transmission mode, for example, X-ray techniques with very good resolution can be used, XMLD, XMCD, etc. So there are numerous other methods that can be used, but these are the ones that are in common use most of the time. So let's review about these techniques. We can observe the presence of magnetic domains indirectly by looking at the magnetic hysteresis curve, magnetic induction versus magnetic field strength curve. We can see discrete jumps that are signatures of domain wall pinning along the path, pinning and depinning of domain walls as they sweep through the specimen. We can use colloidal suspension of ferromagnetic particles on electropolished, so that removes the strains. This is done to remove strains from the film, that reduces the magnetic domain sizes. And we can see nice domain wall structure on the surface of the film. We can use magnetooptic Kerr effect. This is based on the rotation of polarization of an incident polarized beam when it interacts with the local magnetic moments at the surface of the film. So we detect the polarization of the reflected light. There is the version where the magnetization is pointing perpendicular to the film plane, polar effect, and we have longitudinal and transverse effects when the magnetization is in the plane of the film, which have a slightly lower signal level. The transmitted light version of this is the Faraday effect. So this is measuring the bulk. If there is enough intensity to measure for the transmitted light here, we can see the domain structure in the bulk of a film, thin magnetic film. Lorentz microscopy in the transmission electron microscope is basically based on the deflection of electrons when they see the local magnetic field gradients inside the film as they're getting transmitted. This has a very good resolution, 5 nanometers or so, and it images the domain walls because the large magnetic field gradients cause deflection of the electrons. Spin polarized scanning electron microscopy, we can look at the number of backscattered electrons at a given angle because it depends on the direction of magnetization within a domain, so interaction of the local moments and the incoming electrons. In the SEM, so it's a surface technique, we can use the diffraction of neutrons. So we can have polarized neutrons that are transmitted through a specimen, and the angle of the rotation of polarization of these neutrons will depend on the magnetization direction. So this is due to the fact that the neutron has a magnetic moment but no charge. So it's the magnetic moment of the neutron that is interacting with the local magnetic moment. But as you can see, it's 4 orders of magnitude lower than a Bohr magneton. Finally, there's another commonly used surface technique, that's magnetic force microscopy. This actually data is one of our own cobalt iron boron film. We have a small tip, radius 10 to 100 nanometers, that is magnetized, so it's covered with magnetic material. We scan it along the surface and we look at the variations in the frequency and phase of oscillations of the tip due to the interaction between the tip magnetization and the local magnetic field gradients. So it images the domain walls, and it has a resolution of the order, typically of the order of 50 nanometers. Other techniques such as X-ray techniques in the synchrotron, XLMD, XMCD, etc., can be used to get more information about these